Sound is everywhere. It shapes the world around us, from the music we love to the technology we use. But what happens when sound pushes its limits? Today, we embark on a journey to explore the science, the speed, and the future of sound, beyond what we ever thought possible. Could we one day fly at Mach 10? Could sound exist in space? And what if we could break the sound barrier without a boom? Stay with us as we uncover the mysteries of sound and speed. Sound is all around us, car engines, conversations and music. But have you ever wondered how fast it actually moves? And what if I told you that in space, sound doesn't even exist? In today's video, we're exploring the fascinating nature of sound waves and the science behind their speed. How fast is sound? The science behind sonic speed. To understand the speed of sound, we first need to understand what sound actually is. Unlike light, which can travel through the vacuum of space, sound needs a medium, like air, water or metal, to move. Why? Because sound is a mechanical wave, meaning it relies on molecules bumping into each other to propagate. When an object vibrates, like a drum or a speaker, it disturbs the molecules around it. These molecules pass energy along to their neighbors, creating a chain reaction of movement, which we perceive as sound. The nature of sound has fascinated scientists for centuries. The ancient Greeks, like Aristotle, believed that sound was carried by the air. But it wasn't until the 17th century that Galileo and Isaac Newton began forming mathematical explanations for how sound moves. In 1660, English scientist Robert Boyle demonstrated that sound cannot travel through a vacuum by placing a ringing bell inside a glass jar and removing the air. This proved that sound waves need a medium to travel. But how fast does sound actually move? That depends on three key factors: the density, elasticity, and temperature of the medium. In dry air at room temperature, sound moves at about 343 meters per second. That's over 1,230 kilometers per hour. But if you're underwater, sound moves about 4 times faster at 1,480 meters per second. And in solids like steel, a staggering 5,960 meters per second. You've probably noticed this delay when you see lightning before you hear thunder. That's because light travels almost 1 million times faster than sound. The speed of sound isn't fixed. It changes based on temperature, pressure, and the type of material it moves through. Warmer air makes molecules move faster, allowing sound waves to travel more quickly. That's why sound moves faster on a hot summer day than on a cold winter night. In water, sound moves faster because water molecules are more tightly packed than air molecules, making it easier for sound waves to transfer energy. The same principle applies to solids. Because their atomic structure is even more compact, sound can travel through them the fastest. From music to medical imaging, from communication to navigation, understanding the speed of sound has led to some of the most important technological advancements of our time. And we're just scratching the surface. So the next time you hear a song, a siren, or even your own voice, remember, you're experiencing a mechanical wave traveling through the air at hundreds of meters per second. Sound is everywhere, but have you ever stopped to think about how it actually moves? Unlike light, which can travel through the vacuum of space, sound needs a medium, like air, water, or metal, to travel. But why does it move faster through some materials and slower through others? Let's break it down. The science behind the speed of sound. Sound travels as a longitudinal wave, meaning that it moves in a series of compressions and rarefactions. Picture a row of dominoes. If you push the first one, the motion transfers down the line. Sound works the same way. The molecules bump into each other, transferring energy as the wave moves forward. This is different from light, which moves as a transverse wave, perpendicular to its direction of travel. Let's compare different types of waves to understand how sound travels through various media. So, how do we measure the speed of sound? It all comes down to this equation. V equals F times lambda. where v is the speed of sound, f is the frequency of the wave, and lambda is the wavelength. Let's break this down. Frequency is how many waves pass a point per second, measured in hertz. Wavelength is the distance between two compressions or two rarefactions. Multiply these together, and you get the speed of sound. Lower frequency waves have longer wavelengths, while higher frequency waves have shorter ones. But no matter the frequency, sound speed depends on something much bigger, the medium it moves through. Not all materials carry sound the same way. The speed of sound changes based on three key properties of the medium: elasticity, density, and temperature. Elasticity materials that are more elastic, like steel, allow sound waves to move faster because their molecules return to their original positions quickly. Density. Denser materials can slow sound down, especially in gases. Heavier gas molecules don't transfer energy as efficiently as lighter ones. Temperature. Warmer temperatures make molecules move faster, increasing the speed of sound. That's why sound moves faster on a hot day than on a cold one. Understanding sound speed isn't just for scientists. It's used in real-world applications every day. Pilots calculate it to avoid sonic booms, submarines rely on it for sonar, and doctors use it in ultrasound machines to see inside the human body. And in future space exploration, understanding how sound behaves in different atmospheres will help us design better technology for exploring planets like Mars. From the vibrations of a guitar string to the roar of a jet engine, the speed of sound is all around us, and now you know the science behind it. Sound is all around us. It moves through the air when we talk, through water when a whale sings, and through metal when a train rumbles down the tracks. But did you know that the speed of sound changes depending on what it's traveling through? Let's break down the science behind this. In gases, sound travels by bouncing from one molecule to another. But not all gases are equal. The speed of sound depends on temperature, density, and the type of gas molecules present. Let's take a look at how sound travels through different gases. In air at 20 degrees Celsius, sound travels at 343 meters per second. In helium, it travels much faster, at 1,000 meters per second. And in carbon dioxide, sound moves at 268 meters per second. Ever wonder why your voice sounds high-pitched after inhaling helium? That's because helium is lighter and less dense than air, allowing sound waves to travel nearly 3 times faster. On the other hand, carbon dioxide is denser than air, so sound moves through it more slowly. That's why speaking into a CO2-filled chamber makes your voice sound deeper. All right, let's talk about pitch changes. Have you ever noticed how your voice sounds different when you inhale helium? It's because helium is less dense than air, causing your vocal cords to vibrate faster and your voice pitch to increase. On the other hand, inhaling carbon dioxide, which is denser than air, slows down the vibration of your vocal cords, lowering your voice pitch. It's a fascinating demonstration of how the medium through which sound travels can affect its properties. So, how does sound travel in liquids? Well, unlike in gases, the molecules in liquids are more closely packed together. This means that sound waves can move through liquids more efficiently and generally at a faster speed. The closer the molecules, the quicker the sound can be transmitted from one molecule to the next. Now let's dive into liquids. Unlike gases, liquids have more tightly packed molecules, making sound travel much faster. But the exact speed depends on how the molecules interact. For example, sound travels faster in water than in oil because water molecules are more tightly bonded. It's these interactions that determine the speed and efficiency of sound transmission in various liquids. Let's take a look at how sound travels through different liquids. In water at 25 degrees Celsius, sound travels at 1,480 meters per second. In seawater, it speeds up to 1,530 meters per second. And in oil, it moves at about 1,400 meters per second. In fresh water, sound moves at almost 1,500 meters per second, 4 times faster than in air. That's why dolphins and whales use sound waves for long-distance communication underwater. Salt water is even denser than fresh water, so sound moves even faster. This is why sonar technology works so well for submarines and deep-sea exploration. Oil, being more viscous, has a slightly different sound speed, but it still allows sound waves to travel far faster than in air. A real-world example, an ultrasound machine using sound waves to image inside the human body. In solids, sound waves travel incredibly fast, much faster than in liquids or gases. This is because the molecules in a solid are tightly packed together, allowing the waves to move quickly from one molecule to the next. Now for the fastest medium, solids, because their molecules are packed even tighter, sound moves incredibly fast. Solid speed of sound, mess wood. 3,300 meters per second glass, 4,540 meters per second steel, 5,960 meters per second. Ever noticed how knocking on wood produces a sharp, fast sound? That's because sound moves through it 10 times faster than through air. Glass is even better at transmitting sound, which is why it's often used in musical instruments like wine glasses that sing when you run a finger around the rim. And here's the champion, steel. Sound zips through steel at nearly 6,000 meters per second. That's why railway workers used to place their ears on train tracks to detect incoming trains long before they could hear them in the air. A person tapping a metal rod and hearing the vibration instantly at the other end. Let's put everything into perspective with this ultimate speed comparison. All right, now let's take a look at a comparison chart summarizing the speeds of sound in different mediums. In air, the speed of sound is 343 meters per second. In water, it's 1,480 meters per second, and in steel it reaches a whopping 5,960 meters per second. As you can see, sound is fastest in solids, slower in liquids, and slowest in gases. But why does this matter? From music production to deep-sea exploration, understanding how sound moves helps us design better technology and improve communication systems. Whether it's the deep hum of a whale call or the sharp clang of metal, the speed of sound is always changing based on its medium. Now, the next time you hear an echo or talk underwater, you'll know exactly why it sounds different. Whether it's the deep hum of a whale call or the sharp clang of metal, the speed of sound is always changing based on its medium. Now, the next time you hear an echo or talk underwater, you'll know exactly why it sounds different. You just heard one of the most powerful sounds in aviation, the sonic boom. But what actually happens when a plane goes faster than sound? And why does it make that deafening noise? Let's break it down. Before we dive into the sonic boom, we need to talk about Mach numbers. In aviation, speed is measured relative to the speed of sound. This is called the Mach number, named after Austrian physicist Ernst Mach. When an aircraft reaches Mach 1, it's moving as fast as sound itself, but going beyond that creates a powerful shockwave, the famous sonic boom. As the fighter jet approaches Mach 1, you can see the sound waves compressing in front of it. This is the build-up to something truly remarkable. Breaking the sound barrier wasn't always possible. For years, engineers believed that supersonic flight would rip an aircraft apart due to intense aerodynamic forces. But in 1947, test pilot Chuck Yeager changed history. Yeager piloted the Bell X-1, a rocket-powered plane designed to handle extreme speeds. On October 14, 1947, he flew at Mach 1.06, becoming the first human to break the sound barrier and creating the first man-made sonic boom. In 1947, the Bell X-1 made history by breaking the sound barrier. As it passed Mach 1, a massive boom echoed through the sky. So, what exactly causes that explosive sound? Normally, sound waves move outward in all directions, but when an aircraft reaches Mach 1, those waves get compressed because the plane is moving as fast as sound itself. This creates a shockwave, a sudden change in air pressure that travels to the ground as a sonic boom. The faster the plane, the more intense the shockwave. But did you know a sonic boom isn't just one sound? It's actually a continuous wave spreading along the flight path, meaning people on the ground hear it at different times. Ever seen this? A white vapor cone forming around a supersonic aircraft? This is called a Prandtl-Glauert condensation cloud. It happens because of sudden pressure drops, causing moisture in the air to condense into visible water droplets. It's not directly related to the sonic boom, but it's an incredible visual effect that happens around the same time. Now, what if I told you that engineers are working on ways to break the sound barrier without a sonic boom? NASA's X-59 Quest is an experimental aircraft designed to fly faster than sound while minimizing the shock waves. Instead of a loud explosion, people on the ground would hear a soft thump. This could revolutionize air travel, bringing back supersonic passenger jets like the Concorde, but much quieter. So we've covered the history, the physics, and even the future of supersonic travel. Now here's a question for you. If you could fly faster than sound, where would you go? Drop your answers in the comments below. Speed has always been one of humanity's greatest obsessions. From the first flight by the Wright brothers to jets that travel faster than sound, we've never stopped pushing the limits. But how fast can we really go? And what challenges stand in the way of extreme speeds? Welcome to the world of supersonic and hypersonic travel. When we talk about high-speed flight, we classify it in two main categories: supersonic and hypersonic. Supersonic, Mach 1 to Mach 5, faster than sound but manageable with current technology. Hypersonic, Mach 5 and beyond, extreme speeds where air behaves very differently. Supersonic speeds have been around for decades, but hypersonic flight is the new frontier, a game-changer for both military and commercial aviation. Let's start with some of the fastest planes ever built. Aircraft that shattered speed records and redefined aviation. Concorde, Mach 2.04, the world's first commercial supersonic jet. It could fly from New York to London in under 3.5 hours, but was retired due to high costs and sonic boom restrictions. SR-71 Blackbird, Mach 3.3 plus, a military reconnaissance plane built for speed and stealth. If a missile was fired at it, it simply outran it. X-51, a Wave Rider, Mach 5 plus hypersonic test jet, an experimental scramjet-powered aircraft designed to sustain hypersonic speeds for minutes at a time. Flying this fast isn't easy. At supersonic and hypersonic speeds, aircraft face three major challenges: heat, fuel consumption, and sonic booms. Heat. The faster a plane moves, the more air friction it experiences. At Mach 3 plus, the SR-71 skin would reach 600 degrees Fahrenheit or 316 degrees Celsius, hot enough to cook a meal. Fuel consumption. The faster you go, the more fuel you burn. Concorde needed tons of fuel just to reach Mach 2. Hypersonic jets need even more efficient propulsion. Sonic booms loud, disruptive, and one of the biggest reasons supersonic flight is restricted over land. Engineers are now working on ways to reduce or eliminate sonic booms for future passenger jets. Despite these challenges, supersonic and hypersonic travel is making a comeback. NASA's X-59 Quest, a supersonic passenger plane designed to fly at Mach 1.4 without producing a disruptive sonic boom. Hypersonic weapons and space travel. The military is investing heavily in hypersonic missiles, and companies like SpaceX are exploring ultra-fast Earth-to-Earth travel. Imagine flying from New York to Tokyo in under an hour. This could be reality in the next few decades. So, we've covered the fastest aircraft, the biggest challenges, and the future of supersonic and hypersonic travel. But now, I want to hear from you. If you could fly anywhere at Mach 5, where would you go? Have you ever wondered what space sounds like? Maybe you've heard the phrase, "In space, no one can hear you scream," and it's true, at least for the most part. Sound needs a medium to travel through, like air, water, or solid materials. And since space is a vacuum, there's no air to carry sound waves. But there's a twist. Scientists have actually detected sound waves in space, and not just any sound, the deepest sound in the universe. Space-time and sound, how sound exists in extreme environments. Sound is just vibrations traveling through a medium. On Earth, air carries those vibrations to our ears, but in space, no air, no sound. That's why in real space there would be no fiery explosion sounds like in sci-fi movies. Inside a spaceship, sure, because there's air. But outside, silence. But wait, what if I told you scientists have recorded a sound wave in space? In 2003, NASA's Chandra X-ray Observatory detected pressure waves rippling through the hot gas surrounding the Perseus galaxy cluster. These waves are technically sound waves. The frequency of these waves is so low, about 57 octaves below middle C, that human ears can't hear it. But if we could, it would be the deepest sound ever recorded. This discovery tells us that even in space, under the right conditions, sound waves can still exist, just not in the way we normally hear them. Even though space is mostly silent, some planets and moons have atmospheres, meaning sound can travel. But it sounds different from Earth. Mars. The air on Mars is 100 times thinner than Earth's and mostly carbon dioxide. This makes sound travel slower, around 240 meters per second compared to Earth's 343 meters per second. Low-pitched sounds are muffled, but high-pitched sounds travel better. Venus. Venus's thick, hot atmosphere is made of carbon dioxide and sulfuric acid clouds. Sound travels much faster than on Earth, about 450 meters per second, meaning you'd hear voices deeper and more distorted. Titan, Saturn's moon, has a dense, nitrogen-rich atmosphere. Sound moves at about 200 meters per second there, which is slower than on Earth. However, the denser air makes sound travel farther. Each of these worlds would have its own unique soundscape, and if we ever sent astronauts there, their voices might sound completely different. Black holes themselves don't make sound, but the gas and material around them do. The sound waves in the Perseus cluster come from a supermassive black hole sending pressure waves through hot plasma. By translating those waves into human hearing range, NASA has heard the voice of a black hole. This eerie sound reminds us that the universe is far from silent. It just sings in a language we're only beginning to understand. So, while space is mostly silent, there are incredible exceptions. From deep cosmic rumbles to alien atmospheres where sound bends and changes, the universe is full of mysteries. Which space object would you love to hear if we could? A black hole? Jupiter's storms? The surface of an exoplanet? Imagine flying from New York to London in just 3 hours. Sounds amazing, right? But for decades, supersonic flight has been limited by one major problem. This. The sonic boom, a powerful, earth-shaking noise that makes supersonic travel over land almost impossible. But what if we could fly faster than sound, without the disruptive boom? Meet NASA's X-59 Quasar, the aircraft designed to make quiet supersonic travel a reality. The future of quiet supersonic flight? When an aircraft travels faster than sound, it pushes air molecules so quickly that pressure waves pile up, forming a loud shock wave, better known as a sonic boom. This phenomenon was first observed in 1947, when Chuck Yeager became the first human to fly faster than sound. But ever since, sonic booms have been a major roadblock for commercial supersonic flight. Concorde, the legendary supersonic passenger jet, was retired in 2003. Why? Its sonic booms were just too disruptive. NASA's X-59 Quest, short for Quiet Supersonic Technology, is a groundbreaking aircraft built to fly supersonic without the boom. But how does it do that? First, the aircraft's ultra-long nose helps spread out shock waves, preventing them from merging into a single boom. Instead of a loud explosion, people on the ground would hear a gentle thump, almost like a distant rumble. The X-59 is designed for shockwave cancellation using carefully shaped wings and fuselage to redirect air in a way that reduces noise. If the X-59's quiet boom technology works, it could pave the way for new supersonic passenger jets. A new generation of planes could fly at Mach 1.5 or faster, without disturbing people on the ground. Imagine flying from Los Angeles to Tokyo in 5 hours, or New York to Paris in 3. But would people be willing to pay for it? And can airlines make it affordable? These are the big questions that need to be answered. NASA isn't the only one investing in silent supersonic technology. Companies like Lockheed Martin, Boeing and DARPA are also researching ways to make supersonic travel more efficient, quiet and practical. Boeing is working on hypersonic passenger jets that could fly at Mach 5 or more, 5 times the speed of sound. And DARPA is testing hypersonic military aircraft that could one day lead to new breakthroughs in aviation. The X-59 is just the beginning. If silent supersonic travel becomes a reality, it could revolutionize global transportation, reducing travel time between continents to just a few hours. But for now, the world is watching as NASA prepares for test flights in 2025. Will it finally bring back the era of supersonic flight? From the perfect acoustics of a concert hall to the deep-sea sonar mapping the ocean floor, sound waves are shaping our world in ways you might not expect. Today, we're diving into the incredible world of sound in modern technology, where physics meets engineering to shape the future. Ever wonder why concert halls sound so perfect, while a simple empty room echoes like crazy? That's where acoustic engineering comes in. Engineers use materials like wood, foam, and diffusers to control sound reflections, so that music sounds crystal clear. This same technology is used in recording, studios, theatres, and even home soundproofing. And it doesn't stop there. Noise barriers along highways help block traffic noise using specially designed panels that absorb and deflect sound waves. But sound doesn't just help us hear better, it helps us see better too. Ultrasound uses high-frequency sound waves to scan inside the human body. These waves bounce off organs, muscles, and even unborn babies, creating detailed images without using harmful radiation. Unlike X-rays, which use radiation, ultrasound is completely safe and is used for everything from pregnancy scans to detecting tumors. And now, scientists are developing 3-dimensional and even 4-dimensional ultrasound technology, giving doctors an even clearer picture of what's happening inside our bodies. Ever wonder how submarines navigate in the dark, deep ocean? Since light doesn't travel well underwater, they use sound waves instead. Sonar, or sound navigation and ranging, works by sending out pulses of sound that bounce off objects and return to the source. This helps submarines detect other vessels, underwater mountains, and even enemy threats. But sonar isn't just for submarines. Scientists use it to map the ocean floor, helping us explore the 97% of the ocean we've never seen. And sonar has even helped uncover shipwrecks and lost treasures deep beneath the waves. Now let's go even bigger, to the scale of entire planets. Did you know that earthquakes send out sound waves just like an explosion? These waves, called seismic waves, travel through the Earth, helping scientists understand what's happening deep underground. There are 2 main types of seismic waves: primary waves or P waves, which are the fastest and travel through both solid and liquid. And then there are secondary waves or S waves, which are slower and travel only through solid rock. By studying these waves, scientists can detect earthquakes, predict tsunamis, and even map the Earth's core. Thanks to seismic technology, we now have early warning systems that save lives by detecting quakes before they strike. From concert halls to submarines, from hospitals to earthquake zones, sound waves are shaping our world in ways we never imagined. And who knows? Maybe one day, we'll even find a way to use sound waves to explore distant planets and moons. From Chuck Yeager's first supersonic flight in 1947 to NASA's X-59 quest, shaping the future of quiet supersonic travel. The race for speed has never slowed down. But how far can we push the limits of speed? Could we one day travel at Mach 10 and beyond? And if so, what would that mean for our world? Before we dive into the future, let's take a quick look at how we got here. Mach 1 breaking the sound barrier, Chuck Yeager's historic 1947 flight, shattered the belief that supersonic travel was impossible. Mach 2 to Mach 3, pushing the limits aircraft like the Concorde and SR-71 Blackbird proved that supersonic flight could be commercial and strategic. Mach 5 plus, the hypersonic era begins. Experimental vehicles like the X-51A Wave Rider have shown that we can reach speeds beyond Mach 5. We've mastered supersonic, we're testing hypersonic, but what comes next? High-speed travel isn't just about speed, it's about changing the way we connect the world. Future supersonic passenger jets could bring back commercial supersonic travel without the noise pollution of the Concorde. Hypersonic military aircraft could change global defense strategies, allowing jets to cross continents in minutes. Space travel and re-entry technology rely on hypersonic aerodynamics to make missions to the Moon, Mars, and beyond possible. And here's the real game-changer combining hypersonic flight with space travel. Could we one day have a plane that flies from New York to Tokyo by briefly leaving Earth's atmosphere? But with great speed comes great responsibility. Noise pollution. Sonic booms caused problems in the past. Could new quiet supersonic technology solve this issue? Fuel consumption. Hypersonic engines require immense energy. Will we develop sustainable fuels to power these speeds? Safety risks. The faster we go, the greater the engineering challenges. How do we ensure safety at Mach 10 and beyond? The future of speed isn't just about breaking records, it's about balancing technology, sustainability and safety. So could we one day travel at Mach 10, 15 or even 20? Scientists are already exploring next-gen propulsion systems, including scramjets, air-breathing engines designed to operate at extreme speeds. Plasma propulsion using ionized gas to generate thrust, potentially unlocking speeds far beyond what traditional engines allow. Anti-gravity and warp technology. Could breakthroughs in quantum physics lead to speeds beyond anything we can imagine? The race for speed is far from over. The big question is, how fast can we go, and what will it mean for the future of travel, science, and even space exploration?